Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the ancient waters that remember everything, Earth's first oceans and the slow rivers of deep time. If you find peace or curiosity in these gentle stories, please consider liking video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The river moves through granite and basalt, carrying with it the dissolved memory of mountains. Each grain of quartz, each flake of mica, settles into layers that will remain undisturbed for millions of years. The water knows nothing of its destination, yet it carries forward the chemical signature of every stone it touches, every mineral it dissolves, every ancient shore it has kissed. This liquid archive flows across continents, gathering the planetary story grain by grain, molecule by molecule. In the laboratory of deep time, rivers function as Earth's circulatory system, moving nutrients and elements across vast distances with the patience of geological ages. They transport iron from continental interiors to ocean basins, phosphorus from weathered peaks to coastal shelves, and carbon from organic decay to marine sediments. Calcium leached from limestone formations travels thousands of miles before precipitating as new rock on distant seafloors. This planetary metabolism operates on scales that dwarf human comprehension. Only took 4 billion years to perfect the recipe. The sediment cores pulled from ocean floors reveal their secrets reluctantly, layer upon microscopic layer. Bands of clay and silt alternate with sequences of calcium carbonate, each stripe a season, each sequence a millennium. Scientists read these archives like books written in mineral script, deciphering climate patterns from the size of sand grains and ocean temperatures from the chemistry of fossilized shells. The oxygen isotopes locked in ancient carbonates whisper of ice ages and warming periods, while rare Earth elements trace the volcanic episodes that punctuated Earth's quiet moments. Modern rivers carry forward this ancient tradition, their waters bearing the chemical fingerprint of the continents they drain. The Amazon transports sediment from the Andes to the Atlantic, its brown plume visible from space as it spreads across the ocean surface. The Mississippi delivers nutrients from the Great Plains to the Gulf of Mexico, feeding marine ecosystems with minerals weathered from rocks formed in Paleozoic seas. Each river system operates as a vast conveyor belt, moving Earth's substance from high places to low places with inexorable persistence. The chemistry of river water tells stories written in parts per million. Dissolved silica speaks of feldspar weathering in mountain watersheds. Sulfate concentrations reveal the oxidation of pyrite in ancient sedimentary formations. Trace metals like strontium and rubidium serve as fingerprints, allowing geochemists to identify the specific rock types contributing to each river's mineral cargo. The ratios remain remarkably consistent over human timescales, yet shift gradually over geological periods as erosion exposes different rock formations to the surface. Yet mysteries remain embedded in the rock record, enigmas that resist easy explanation. Why do certain elements concentrate in patterns that seem to defy conventional weathering models? How did early rivers maintain their flow across landscapes that bore no resemblance to modern topography, when atmospheric composition and rainfall patterns differed dramatically from today's climate? The stones keep their counsel, revealing truth only to those patient enough to measure time in geological increments and humble enough to accept uncertainty as a fundamental aspect of deep time inquiry. The mathematics of river transport operate according to principles discovered through patient observation. Hjulström's curve describes the relationship between water velocity and particle size, explaining why swift mountain streams carry boulders while gentle coastal rivers deposit fine silt. The Shields parameter quantifies the threshold of motion for sediment grains, predicting when particles will begin their journey toward the sea. These equations apply equally to modern watersheds and ancient river systems preserved in the geological record. Paleo-rivers leave subtle traces in the landscape, their former paths etched into bedrock surfaces now buried beneath younger sediments. Geologists map these buried channels using seismic surveys, revealing drainage networks that operated millions of years ago under different continental configurations. Some ancient rivers flowed in directions opposite to modern streams, their courses determined by mountain ranges that have since eroded away and ocean basins that have long since closed. The isotopic signature of river sediments preserves evidence of past climatic conditions with startling precision. During glacial periods, rivers carried different mineral assemblages as ice sheets exposed fresh bedrock to weathering. Tropical rivers deposited clay-rich sediments formed under intense chemical weathering, while rivers in cold climates transported mechanically weathered rock fragments with minimal chemical alteration. These sedimentary archives allow reconstruction of ancient climate zones with remarkable detail, like a planetary circulatory system. These ancient waterways pulse with the rhythm of erosion and deposition, each flood season adding another page to Earth's autobiography. The cycle continues today as it has for billions of years, water falling as rain, gathering into streams, converging into rivers, carrying dissolved continents toward the sea. In this endless circulation, every drop of water has crossed countless landscapes, touched innumerable stones, and participated in the slow but persistent process of planetary renewal. The river remembers everything, carrying forward the accumulated wisdom of deep time in its quiet, persistent flow toward the ocean that waits at the end of all journeys. 4 billion years ago, the sky holds no blue. Above the young Earth, a thick atmosphere of carbon dioxide and water vapor presses down upon a surface still glowing with the heat of planetary formation. The temperature hovers near the boiling point of water, and steam rises from every impact crater, every volcanic vent, every cooling lava flow. This is the moment when Earth's first ocean begins its quiet birth from the cooling breath of stone. The water vapor condenses slowly, molecule by molecule. As the planet's surface temperature drops below the critical threshold, each droplet forms around microscopic particles of dust and volcanic ash suspended in the dense atmosphere. Gravity pulls these droplets downward through the scorching air, where many evaporate before reaching the ground, only to condense again higher in the atmosphere. This process repeats countless times, a planetary distillation that gradually concentrates water vapor into larger and larger droplets. The first raindrops to survive the journey to Earth's surface hiss into steam upon contact with the hot basalt. But the planet continues cooling, and eventually the drops linger long enough to pool in the low places between volcanic ridges. These earliest puddles last only hours or days before boiling away, yet they represent the first liquid water to exist on Earth's surface since the planet's formation. Only took several 100 million years to figure out the recipe for staying liquid. Steam devils spiral upward from the warming rock, carrying dissolved minerals into the atmosphere where they precipitate as microscopic crystals. The early water cycle operates under conditions unknown on modern Earth, with surface pressures many times greater than today's atmosphere and temperatures that would be lethal to any known form of life. Yet this alien water cycle begins the slow process of chemical weathering that will eventually create the complex chemistry necessary for life itself. The basaltic crust reacts with liquid water to form the first clay minerals on Earth's surface. Olivine and pyroxene crystals, formed in the high-temperature environment of magma chambers, encounter water and begin their transformation into serpentine and other hydrated silicate minerals. This process releases hydrogen gas into the early atmosphere while consuming water molecules, creating a chemical balance that will persist for billions of years. Impact craters serve as the first ocean basins, their floors lined with impact breccia and volcanic glass. Asteroids and comets continue to bombard the cooling surface, each collision vaporizing any accumulated water, but also delivering additional water ice from the outer solar system. The larger impacts create temporary atmospheric plumes of superheated steam that can persist for centuries before condensing back to the surface. The bombardment gradually decreases in intensity, allowing water to accumulate in progressively longer-lived bodies. The chemistry of these primordial waters differs dramatically from modern seawater. Dissolved iron concentrations reach levels thousands of times higher than today's oceans, giving the early seas a reddish-brown coloration. Sulfur compounds from volcanic gases create acidic conditions that accelerate rock weathering. Dissolved carbon dioxide maintains a pH far more acidic than modern seawater. Yet these harsh conditions prove essential for the chemical processes that will eventually generate the diversity of elements necessary for biological complexity. Scientists study this ancient ocean chemistry through the analysis of komatiite lavas, volcanic rocks that preserve chemical signatures from Earth's early mantle. These ultramafic rocks contain mineral assemblages that formed only under the extreme temperature conditions of the Archean era. The komatiites also preserve tiny inclusions of ancient seawater, trapped within crystallizing minerals 4 billion years ago. These inclusions provide direct evidence of early ocean composition, though interpreting their chemistry requires careful consideration of subsequent alteration processes. Yet, fundamental questions remain unanswered about Earth's first ocean. How did the early atmosphere maintain sufficient pressure to keep water liquid at temperatures near the boiling point? What role did dissolved greenhouse gases play in stabilizing early climate conditions? The trace element signatures preserved in ancient rocks suggest complex interactions between atmosphere, ocean, and solid Earth that operated under conditions never again repeated in Earth's history. The early ocean's thermal structure differs radically from modern seas. Without solar heating driving surface temperature gradients, the primitive ocean likely maintained relatively uniform temperatures from surface to sea floor. Convection cells driven by geothermal heating from the seafloor create circulation patterns unlike anything observed in modern oceans. Dissolved minerals precipitate directly from seawater as temperatures fluctuate, creating chemical sediments that accumulate on the ocean floor without biological mediation. Tidal forces from the nearby moon, still much closer to Earth than today, create massive bore tides that sweep across the shallow seas. These tides reach heights measured in hundreds of meters, mixing the ocean chemistry and preventing the development of stable chemical gradients. The rapid tidal cycling accelerates chemical reactions between seawater and seafloor basalt, pumping dissolved elements into the ocean faster than modern processes can achieve. The absence of continental landmasses means that all chemical weathering occurs through direct seawater basalt interaction. Hydrothermal vents provide the primary source of dissolved elements, creating chemical plumes that spread across ocean basins. These underwater hot springs operate at temperatures exceeding 400 degrees Celsius, far hotter than modern hydrothermal systems. The extreme conditions drive unusual mineral precipitation processes that create exotic seafloor deposits unlike anything found in younger geological formations, like a planetary baptism. This first ocean marks Earth's transition from a molten ball of rock to a world capable of sustaining liquid water. The process unfolds over hundreds of millions of years, each cooling degree allowing water to persist a little longer, accumulate a little deeper, interact a little more completely with the mineral foundation of the planet. In this patient cooling lies the beginning of all subsequent Earth history, the moment when our planet first learned to hold water in its embrace and began the long journey toward becoming a living world. The young ocean tastes of metal and sulfur, its chemistry a harsh brew that would corrode modern marine life within moments. Yet, in this alien sea, time works its patient alchemy, concentrating minerals through the slow dance of evaporation and dissolution. Salt crystals begin their billion-year accumulation as the planet's water cycle finds its rhythm between sea and sky. Evaporation from the early ocean's surface operates under atmospheric conditions far different from today's climate. The dense carbon dioxide atmosphere creates a greenhouse effect that maintains surface temperatures near the boiling point of water, driving intense evaporation rates that concentrate dissolved minerals in the remaining seawater. As water vapor rises through the thick atmosphere, it carries with it trace amounts of volatile elements, leaving behind increasingly concentrated brines in isolated basins and tidal pools. The first salt deposits form in shallow embayments where evaporation exceeds input from rainfall and runoff. These primitive evaporates consist mainly of sulfate minerals like gypsum and anhydrite, precipitated from seawater with sulfur concentrations far exceeding modern levels. Halite, common table salt, remains rare in these early deposits because the ocean's sodium to chloride ratio differs dramatically from today's seawater composition. The evaporate sequences accumulate in layers only millimeters thick, each representing decades or centuries of patient mineral precipitation. Hydrothermal circulation through the oceanic crust drives massive elemental exchanges between seawater and basaltic rock. Cold seawater penetrates fractures in the seafloor, where it heats to temperatures exceeding 400 degrees Celsius before returning to the ocean surface laden with dissolved metals. This hydrothermal flux delivers iron, manganese, copper, and zinc to the early ocean at rates thousands of times higher than modern systems. The metals remain dissolved in the oxygen-free water, creating a planetary-scale ore solution that will eventually precipitate when ocean chemistry changes. The absence of continents means that chemical weathering occurs entirely through seawater rock interaction. Basaltic glass on the seafloor reacts with seawater to form clay minerals, consuming hydrogen ions and making the ocean less acidic over geological time. This weathering process releases calcium, magnesium, and potassium into seawater while removing carbon dioxide from the ocean atmosphere system. The reaction rates depend critically on temperature, accelerating dramatically in the hot conditions of the early Earth. Tidal evaporation creates vast salt flats in the shallow margins of the early ocean. Twice daily, massive tides driven by the nearby moon expose seafloor sediments to the hot atmosphere, where rapid evaporation precipitates mineral crusts of unusual composition. These tidal flats extend for hundreds of kilometers inland, their surfaces encrusted with sulfate and carbonate minerals that form geometric patterns as crystallization follows natural fracture systems in the drying sediment. Scientists study these ancient evaporate processes through the analysis of fluid inclusions trapped within halite crystals from Precambrian salt deposits. These microscopic capsules of ancient seawater preserve chemical signatures from billions of years ago. Though interpreting their composition requires careful consideration of post-depositional changes, The inclusions contain unusual ratios of dissolved elements that reflect the exotic chemistry of Earth's early ocean, including surprisingly high concentrations of metals that would be toxic to modern marine organisms. Yet, fundamental uncertainties persist about the mechanisms of early ocean concentration. How did the primitive water cycle maintain chemical balance between evaporation and precipitation over geological timescales? What role did early atmospheric composition play in controlling evaporation rates and mineral solubility? The trace element patterns preserved in ancient evaporates suggest complex feedback mechanisms between ocean chemistry, atmospheric composition, and crustal weathering that operated under conditions never repeated in Earth's subsequent history. The early ocean's salinity increases gradually through geological time as evaporation concentrates dissolved minerals faster than dilution by rainfall and hydrothermal input. This concentration process operates with the patience of deep time, each evaporation cycle leaving behind a slightly more concentrated brine. The process accelerates during periods of enhanced volcanism, when increased atmospheric carbon dioxide drives higher evaporation rates, and slows during impact events that temporarily vaporize portions of the ocean and reset the concentration process. Mineral precipitation follows complex sequences as different compounds reach saturation in the concentrating brines. Calcium carbonate precipitates first, followed by calcium sulfate, then sodium chloride, and finally highly soluble salts like magnesium and potassium sulfates. These precipitation sequences create distinctive layered deposits that geologists use to reconstruct ancient ocean chemistry and evaporation conditions. The layering reflects seasonal or longer-term climate cycles that controlled evaporation and dilution in early ocean basins. Salt dome formation begins early in Earth's history as thick evaporate sequences accumulate in restricted basins. The buried salt layers become gravitationally unstable, rising as plastic diapirs through overlying sedimentary rocks. These salt domes create complex geological structures that trap hydrocarbons and host important mineral deposits. Some Precambrian salt domes continue rising today, testament to the long-term mobility of evaporate minerals deposited billions of years ago. The chemistry of early brines differs fundamentally from modern evaporated seawater due to the absence of biological processes that modify ocean composition. No organisms extract calcium carbonate to build shells. No photosynthetic bacteria release oxygen to precipitate iron oxides. No organic matter decomposes to influence pH and redox conditions. The purely inorganic chemistry of early evaporation creates mineral assemblages unknown in younger geological formations, like a planetary kitchen slowly reducing a vast soup. The early ocean concentrates its chemical ingredients through patient evaporation and circulation. Only took 1 billion years for the recipe to approach something resembling modern seawater composition. The process continues today in isolated basins and shallow seas, where evaporation still concentrates dissolved minerals according to the same physical and chemical principles that operated on the early Earth. In the crystalline structure of every salt grain lies encoded the memory of ancient seas and the patient work of time itself. When continents were islands, the Earth presents a geography unrecognizable to modern eyes. Scattered fragments of ancient crust drift across a vast, unbroken ocean that stretches from pole to pole, interrupted only by volcanic archipelagos and the occasional emergence of primitive land masses. These proto-continents, no larger than modern Australia, float like granite rafts on the basaltic sea floor, their edges constantly modified by the relentless action of waves and chemical weathering. The earliest continental crust forms through a process still debated among geologists. Partial melting of basaltic oceanic crust creates granitic magmas that solidify into less dense rocks capable of floating permanently above sea level. These granitic bodies, called tonalite-trondhjemite granodiorite complexes, represent Earth's first successful experiment in creating permanent landmasses. The process requires specific temperature and pressure conditions that existed only during Earth's early history, when higher internal heat flow drove more vigorous mantle convection. Plate tectonics operates differently on the early Earth, with smaller, more numerous plates moving at faster velocities across the planet's surface. The higher heat flow from radioactive decay drives more rapid seafloor spreading and more frequent volcanic eruptions. Continental fragments collide and separate on timescales of tens of millions of years rather than the hundreds of millions of years typical of later geological periods. This rapid crustal recycling prevents the formation of large, stable continents for the first billion years of Earth's history. The scattered protocontinents experience extreme tidal ranges due to the Moon's proximity and the absence of continental barriers to tidal flow. Tides reaching heights of several hundred meters sweep across the low-lying landmasses twice daily, creating vast intertidal zones where early chemical weathering processes operate under alternating subaerial and submarine conditions. These extreme tidal environments accelerate rock breakdown and create unique sedimentary deposits unknown in later geological periods. Weathering of the primitive continents proceeds through purely chemical processes in the absence of soil-forming organisms and land plants. Granitic rocks react with acidic rainwater and seawater to produce clay minerals, releasing dissolved silica, aluminum, and alkali metals to the surrounding ocean. The weathering rates exceed modern continental weathering by factors of 10 or more due to the higher atmospheric carbon dioxide concentrations and elevated temperatures that characterize the early Earth. The ocean between these continental fragments maintains chemical uniformity due to unrestricted circulation. Without large land masses to deflect ocean currents, water masses mix freely across the globe, preventing the development of regional chemical differences that characterize modern ocean basins. This global ocean serves as a vast chemical reactor, homogenizing dissolved elements delivered by weathering and hydrothermal activity across the entire planetary surface. Scientists reconstruct early continental configurations through the analysis of detrital zircon grains preserved in ancient sedimentary rocks. These microscopic crystals, resistant to weathering and metamorphism, preserve uranium-lead isotopic signatures that reveal the age and composition of their source rocks. Detrital zircon populations from different sedimentary basins provide evidence for continental proximity and separation over geological time, allowing geologists to track the motion of ancient landmasses across the early Earth. Yet significant uncertainties remain about early continental evolution. How did the first continental crust achieve sufficient thickness to remain permanently above sea level? What mechanisms controlled the size and distribution of early land masses? The preserved geological record from this period remains fragmentary, with most early continental rocks destroyed by subsequent erosion, metamorphism, and tectonic recycling. Only small portions of the original continental crust survive in highly deformed fragments known as cratons. The volcanic islands that dot the early ocean provide temporary stepping stones for chemical exchange between sea and sky. These volcanic edifices, built by hotspot activity and seafloor spreading, rise kilometers above the ocean's surface before erosion and subsidence return them to the depths. Their brief existence above sea level creates unique environments where subaerial volcanism interacts with seawater to produce distinctive alteration mineral assemblages. Submarine volcanism dominates early Earth's geological activity, with vast outpourings of basaltic lava creating oceanic plateaus that temporarily rise above sea level. These large igneous provinces, similar to modern oceanic plateaus like the Ontong Java Plateau, represent some of the largest volcanic events in Earth's history. Their formation temporarily disrupts ocean circulation and atmospheric composition, creating brief periods of accelerated chemical weathering and climate change. The chemistry of weathering products from early continents differs markedly from modern continental erosion due to the unusual composition of early continental crust. Higher concentrations of mafic minerals in early granitic rocks produce weathering solutions enriched in iron, magnesium, and trace metals compared to modern river water. These metal-rich weathering products contribute to the high dissolved iron concentrations that characterize early ocean chemistry. Erosion rates on early continents exceed modern rates due to the absence of vegetation and soil development. Without plant roots to stabilize surface materials and organic matter to bind soil particles, mechanical erosion proceeds rapidly under the influence of intense storms and extreme temperature fluctuations. The eroded material accumulates as thick sedimentary sequences in adjacent ocean basins, preserving a record of early continental composition and weathering processes. The isolation of early continental fragments creates opportunities for unique evolutionary experiments in crustal development. Each proto-continent develops its own geological history of volcanism, metamorphism, and sedimentation, creating diverse rock assemblages that reflect local conditions. Some fragments develop thick sedimentary sequences, others experience extensive granitic intrusion, and still others undergo high-grade metamorphism that transforms their original compositions beyond recognition. Like geological seeds scattered across a planetary ocean, these early continental fragments carry within their crystalline structure the genetic code for future continental growth. Only took 2 billion years for these scattered islands to aggregate into the first supercontinent. The process of continental assembly and dispersal continues today. Driven by the same plate tectonic forces that operated on the early Earth, though at slower rates and larger scales than the rapid continental dance of deep time, the breath of stone and water mingles in the early atmosphere as volcanic outgassing continues to feed the planet's chemical envelope with new compounds delivered from the deep interior. Each eruption releases a complex mixture of water vapor, carbon dioxide, sulfur gases, and trace elements that slowly accumulate in the thickening atmosphere. This planetary exhalation operates on geological timescales, each volcanic episode adding another increment to the atmospheric inventory that will sustain liquid water and drive chemical weathering for billions of years. Volcanic gases emerge from the mantle carrying isotopic signatures that reveal their deep origins. Helium-3, rare on Earth's surface but abundant in the mantle, provides evidence for primordial gases trapped since planetary formation. Argon isotopes distinguish between atmospheric argon derived from radioactive decay in crustal rocks and mantle argon inherited from the solar nebula. These noble gas signatures allow geochemists to trace the proportion of atmospheric gases derived from different planetary reservoirs over Earth's history. The composition of volcanic outgassing changes gradually as the planet's interior evolves through radioactive cooling and differentiation. Early volcanic emissions contain higher concentrations of reducing gases like hydrogen and methane, reflecting the more reducing conditions in the primitive mantle. As oxygen begins to accumulate in the atmosphere, volcanic gases become increasingly oxidized, with sulfur dioxide replacing hydrogen sulfide and carbon dioxide dominating over methane and hydrogen. Sulfur compounds from volcanic outgassing create a global atmospheric chemistry dominated by sulfuric acid aerosols. These microscopic droplets scatter incoming solar radiation and participate in complex photochemical reactions that influence atmospheric temperature and chemical composition. The sulfur cycle operates without biological mediation, with volcanic sulfur dioxide converting to sulfuric acid in the atmosphere before returning to the surface as acid rain that accelerates rock weathering. The early carbon cycle operates through purely inorganic processes as volcanic carbon dioxide dissolves in seawater to form carbonic acid. This weak acid enhances chemical weathering of basaltic rocks, consuming atmospheric carbon dioxide and releasing dissolved ions to the ocean. The weathering products eventually precipitate as carbonate minerals on the seafloor, completing a carbon cycle that regulates atmospheric composition over geological timescales. Only took several 100 million years to establish this planetary thermostat. Water vapor from volcanic outgassing supplements the atmospheric inventory inherited from cometary bombardment and planetary accretion. Isotopic analysis of volcanic water reveals contributions from multiple sources, including water trapped in hydrated minerals during planetary formation and water delivered by subsequent cometary impacts. The volcanic water cycle gradually replaces the original atmospheric water inventory, as surface water cycles through the mantle via subduction and returns to the surface through volcanic emissions. Scientists study ancient volcanic outgassing through the analysis of gas inclusions trapped in volcanic glasses and mineral crystals. These microscopic samples preserve snapshots of volcanic gas composition from billions of years ago, though interpreting their chemistry requires careful consideration of post-entrapment modifications. The inclusions reveal surprising diversity in ancient volcanic gas compositions, reflecting variations in mantle source regions and eruption conditions that operated under different atmospheric and oceanic environments. Yet, fundamental questions persist about the efficiency and timing of early atmospheric evolution. How did volcanic outgassing rates change as planetary heat production declined through radioactive decay? What role did impact events play in temporarily depleting or enhancing atmospheric inventories? The geological record preserves only indirect evidence of atmospheric composition, requiring complex models to reconstruct the evolution of Earth's early atmospheric chemistry. The rate of volcanic outgassing depends critically on the style and frequency of volcanic eruptions, which change dramatically as plate tectonics evolves from early rapid circulation to more mature, slower plate motions. Higher heat flow on the early Earth drives more frequent and voluminous eruptions, creating massive volcanic provinces that release enormous quantities of gas to the atmosphere. These large igneous province eruptions can temporarily overwhelm atmospheric buffering capacity, creating brief periods of extreme greenhouse conditions. Mid-ocean ridge volcanism provides a continuous source of volcanic gases to the early atmosphere through seafloor, spreading, and hydrothermal activity. The higher spreading rates on early Earth create more extensive ridge systems that outgas at rates several times higher than modern mid-ocean ridges. This enhanced ridge volcanism maintains elevated atmospheric carbon dioxide concentrations that help stabilize liquid water, despite the fainter young sun's reduced luminosity. Volcanic outgassing also delivers trace gases that play important roles in atmospheric photochemistry and climate regulation. Hydrogen escapes to space, gradually oxidizing the atmosphere and ocean system. Chlorine and fluorine compounds participate in stratospheric chemistry that influences atmospheric temperature structure. Trace metals like mercury and lead cycle between volcanic sources and atmospheric sinks, creating global atmospheric pollution long before human industrial activity. The interaction between volcanic gases and seawater creates complex chemical equilibria that buffer ocean pH and alkalinity. Acid volcanic gases neutralize the alkaline products of rock weathering, maintaining ocean chemistry within ranges that allow mineral precipitation and dissolution to proceed. This chemical buffering operates as a planetary homeostatic mechanism that prevents runaway acidification or alkalinization of the early ocean. Atmospheric escape processes remove light gases like hydrogen and helium to space, gradually changing atmospheric composition over billion-year timescales. The escape rates depend on atmospheric temperature and the strength of Earth's magnetic field, both of which differ significantly between early and modern Earth. Higher atmospheric temperatures on early Earth enhance escape rates, while the developing magnetic field provides increasing protection from solar wind stripping of atmospheric gases. Like a planetary respiratory system, volcanic outgassing and atmospheric escape establish the rhythm of atmospheric evolution that continues today. The breath of stone rises from volcanic vents and mid-ocean ridges, carrying the chemical essence of Earth's interior to the surface where it mingles with water and sunlight to create the conditions necessary for chemical complexity. In this endless exchange between solid Earth and atmospheric envelope lies the foundation for all subsequent atmospheric evolution, including the oxygenation events that will transform planetary chemistry and enable the emergence of complex life. Tidal rhythms before the moon's retreat create a hypnotic dance across the early Earth's ocean surface, where gravitational forces far stronger than today's generate massive water movements that reshape coastlines twice each day. The moon hangs much closer to Earth in the early sky, perhaps only half its current distance, exerting tidal forces 8 times more powerful than modern tides. These primordial tides reach heights measured in hundreds of meters, creating a liquid metronome that beats against the scattered continental fragments with relentless precision. The physics of early tidal dynamics operate under conditions unknown to modern oceanography. With the moon orbiting Earth every 10 hours instead of today's 28-day cycle, tidal periods compress into rapid sequences of flooding and exposure that transform vast areas of sea floor into temporary land twice per day. The tidal bulges race around the planet at velocities approaching the speed of sound in water, creating massive hydraulic forces that carve channels through bedrock and transport sediments across continental shelves. Early Earth's rapid rotation, with days lasting only 6 hours, creates complex interference patterns between tidal forces and planetary rotation. The Coriolis effect operates more strongly on the rapidly spinning planet, deflecting tidal currents into spiral patterns that differ dramatically from modern tidal circulation. These enhanced Coriolis forces prevent simple tidal bulges from forming, instead creating complex standing wave patterns that focus tidal energy into specific geographic regions. The absence of large continental barriers allows tidal waves to propagate freely around the global ocean, creating planetary-scale resonances that amplify tidal ranges in certain regions while dampening them in others. These tidal resonances shift gradually as continental fragments drift across the ocean surface, periodically aligning in configurations that create extreme tidal amplification. Some regions experience tidal ranges exceeding 1 kilometer, while others remain relatively calm despite the proximity of the moon. Tidal dissipation through friction with the seafloor and internal waves gradually slows Earth's rotation and pushes the moon into higher orbits. This tidal evolution operates over hundreds of millions of years, with the early rapid changes gradually slowing as the moon recedes and rotational energy dissipates. The process represents one of the largest energy transfers in the solar system, with rotational kinetic energy converting to heat through tidal friction at rates billions of times greater than modern tidal heating. The extreme tidal environment creates unique ecological niches in the vast intertidal zones that extend for hundreds of kilometers inland from the ocean margins. These regularly flooded regions experience rapid chemical weathering as seawater alternately soaks into and evaporates from exposed sediments. The chemical gradients created by this tidal pumping drive unusual mineral precipitation patterns and create microenvironments with chemical conditions that differ dramatically from both permanent ocean and permanent land. Scientists study ancient tidal patterns through the analysis of rhythmites, sedimentary rocks that preserve daily, monthly, and annual cycles in their layering patterns. These tidal archives reveal information about Earth-Moon dynamics over geological time, showing the gradual evolution of tidal periods and rotational rates. The rhythmites also preserve evidence of ancient tidal ranges through the thickness and extent of tidal flat deposits, though interpreting these records requires careful consideration of local basin geometry and preservation conditions. Yet significant uncertainties remain about early tidal dynamics and their effects on planetary evolution. How did extreme tidal mixing influence early ocean chemistry and circulation patterns? What role did tidal heating play in maintaining liquid water during periods of reduced solar luminosity? The complex interactions between tidal forces, atmospheric dynamics, and ocean chemistry create feedback loops that remain poorly understood even for modern Earth conditions. Tidal heating of the early ocean contributes significantly to planetary energy balance, with mechanical energy from tidal friction converting to heat that warms both ocean water and seafloor sediments. This internal heating source helps maintain liquid water during the faint young sun period, when reduced solar luminosity would otherwise freeze the planetary surface. The tidal heating rates decline exponentially as the moon recedes, creating a gradually diminishing internal heat source that influences long-term climate evolution. The massive tidal currents generated by early Earth-Moon dynamics create powerful mixing that homogenizes ocean chemistry on timescales much shorter than modern ocean circulation. These vigorous currents prevent the development of stratified water masses and maintain uniform chemical conditions throughout the global ocean. The enhanced mixing also accelerates chemical reactions between seawater and seafloor rocks, driving higher rates of elemental exchange than occur in modern ocean basins. Tidal bore phenomena reach extreme proportions on early Earth, with advancing tide fronts creating walls of water several hundred meters high that surge across continental shelves at velocities approaching 100 kilometers per hour. These hyperbolic tidal bores carry enormous amounts of sediment and dissolved chemicals, depositing distinctive sedimentary sequences that preserve evidence of their passage. The bore deposits create some of the earliest recognizable sedimentary structures in the geological record. The gravitational interaction between Earth and Moon during close approach creates tidal bulges in the solid Earth as well as the ocean, with rocky tides reaching amplitudes of several meters. This solid Earth tidal deformation generates additional heat through internal friction and influences volcanic activity patterns. Some researchers propose that tidal stress variations triggered enhanced volcanism during periods of close lunar approach, though this hypothesis remains difficult to test through geological observations. Atmospheric tides also operate more strongly on early Earth due to enhanced gravitational forcing and different atmospheric composition and density. These atmospheric tidal oscillations create pressure variations that influence weather patterns and atmospheric circulation in ways unknown on modern Earth. The coupling between oceanic and atmospheric tides creates complex resonance patterns that modulate both marine and atmospheric chemistry over daily and seasonal cycles, like a cosmic clock wound too tightly. The early Earth-Moon system gradually releases its excess energy through tidal friction, slowly evolving toward the more sedate rhythm of modern tides. Only took 3 billion years for the Moon to retreat to a comfortable distance. The process continues today as tidal forces slowly lengthen Earth's days and push the Moon into ever higher orbits, though at rates imperceptible within human lifetimes. In the rhythm of modern tides echoes the memory of that ancient hypnotic dance, when water and gravity conspired to reshape the planetary surface twice each day with the patience and persistence of deep time itself. Iron rust in ancient waters paints the early ocean a deep reddish brown. Its color derived from dissolved metals that would be toxic to modern marine life, but flow freely through the oxygen-free seas of deep time. Ferrous iron, leached from basaltic seafloor and delivered by hydrothermal vents, accumulates to concentrations thousands of times higher than modern seawater can sustain. This liquid ore solution carries within its chemistry the potential for massive mineral deposits that will eventually transform the planet's surface and atmosphere. The solubility of iron in early seawater depends critically on the absence of dissolved oxygen, which would immediately precipitate iron as insoluble oxides. Under the reducing conditions of the Archean Ocean, iron remains dissolved as ferrous ions that impart their distinctive coloration to the water. The iron concentrations reach levels approaching those found in modern industrial ore solutions, creating a planetary-scale hydrometallurgical system operating without biological mediation. Hydrothermal circulation through mid-ocean ridges delivers iron to the early ocean at rates far exceeding modern fluxes. The higher heat flow and more vigorous convection of early Earth drive more extensive hydrothermal systems that leach iron from basaltic rocks and transport it to the seafloor. Black smoke events release iron-rich fluids at temperatures exceeding 400 degrees Celsius, creating hydrothermal plumes that spread dissolved metals across entire ocean basins. The chemistry of iron transport in early seawater involves complex interactions with sulfur compounds and organic molecules that influence metal solubility and bioavailability. Dissolved hydrogen sulfide from volcanic outgassing and bacterial metabolism forms iron sulfide complexes that enhance ion mobility in seawater. These sulfide complexes also create distinctive black precipitates when hydrothermal fluids mix with seawater, forming some of the earliest mineral deposits on Earth's seafloor. Weathering of iron-bearing minerals on early continental fragments contributes additional dissolved iron to the ocean through chemical breakdown of olivine, pyroxene, and magnetite. The acidic conditions created by high atmospheric carbon dioxide concentrations accelerate this weathering process, releasing iron along with other trace metals to rivers that drain into the global ocean. The lack of vegetation and soil development means that weathering products reach the ocean with minimal modification or retention on land. The distribution of dissolved iron in early seawater creates chemical gradients that influence mineral precipitation patterns and biological activity. Iron concentrations vary with depth, distance from hydrothermal sources, and proximity to continental weathering inputs. These spatial variations in iron availability create microenvironments with different chemical conditions that may have influenced early evolutionary processes and metabolic innovations. Scientists study ancient iron chemistry through the analysis of banded iron formations, distinctive sedimentary rocks that preserve evidence of early ocean iron concentrations. These formations consist of alternating layers of iron-rich and iron-poor minerals that record fluctuations in ocean chemistry over geological time. The iron minerals include magnetite, hematite, and siderite, each reflecting different redox conditions during precipitation. Only took 2 billion years to deposit most of the world's iron ore reserves. Yet fundamental questions remain about iron cycling in early ocean systems. How did dissolved iron concentrations remain stable over geological timescales without biological regulation? What mechanisms controlled iron precipitation before the evolution of oxygen-producing organisms? The trace element signatures associated with iron in ancient rocks suggest complex biogeochemical cycles that operated under conditions unlike any modern marine environment. The high iron concentrations in early seawater create opportunities for unusual mineral precipitation processes that rarely occur in modern marine environments. Direct precipitation of iron carbonate minerals like siderite occurs when dissolved iron reacts with carbonic acid in seawater. Iron silicate minerals form through reaction with dissolved silica from weathering and hydrothermal sources. These iron-bearing minerals accumulate as chemical sediments on the seafloor, creating distinctive rock formations that preserve records of early ocean chemistry. Biological interactions with dissolved iron begin early in Earth's history, as primitive organisms evolve metabolic pathways that utilize iron for energy production. Iron-reducing bacteria consume organic matter while using ferric iron as an electron acceptor. Producing ferrous iron as a metabolic byproduct, iron-oxidizing bacteria perform the reverse reaction, gaining energy by oxidizing ferrous iron to ferric compounds. These early iron-based metabolisms operate in the interface zones between oxidized and reduced environments. The transport of dissolved iron by ocean currents creates planetary-scale iron distribution patterns that influence biological productivity and mineral deposition across different ocean basins. Iron-rich waters from hydrothermal regions spread across the ocean surface through wind-driven circulation and thermohaline convection. The iron serves as an essential micronutrient for early photosynthetic organisms, though in concentrations that would be toxic to most modern marine life. Seasonal variations in iron supply create temporal patterns in ocean chemistry that influence biological activity and mineral precipitation. Enhanced hydrothermal activity during periods of increased volcanism delivers pulses of dissolved iron to the ocean. Variations in continental weathering due to climate fluctuations modulate iron input from terrestrial sources. These temporal variations create cyclic patterns in sedimentary iron deposits that preserve records of ancient environmental change. The interaction between dissolved iron and other trace metals in early seawater creates complex chemical equilibria that influence the bioavailability of essential elements. Competition between iron and other metals for binding sites on organic molecules affects nutrient cycling and biological productivity. The high iron concentrations may have influenced the evolution of metalloenzymes and other metal-dependent biological processes that remain essential to modern life, like blood flowing through the arteries of an ancient planet. Iron-rich seawater circulates through the early ocean, carrying the dissolved essence of continents and seafloor to every corner of the global sea. The iron will not remain dissolved forever. Already the first oxygen-producing organisms begin their work in shallow waters, preparing to transform this liquid ore solution into the solid mineral deposits that will serve as humanity's primary iron ore reserves billions of years in the future. In the rusty hue of ancient waters lies encoded the future wealth of civilizations yet to come. The great poisoning begins not with industrial smokestacks or chemical spills, but with the quiet photosynthesis of cyanobacteria that start releasing oxygen into an ocean, an atmosphere utterly unprepared for this reactive gas. These microscopic organisms, no larger than modern bacteria, initiate the most dramatic chemical transformation in Earth's history through their simple biological innovation of splitting water molecules to harvest sunlight. The oxygen they produce as a waste product will eventually become essential for complex life. But first, it must poison nearly everything alive on the early Earth. Cyanobacteria evolved the biochemical machinery of oxygenic photosynthesis around 3.5 billion years ago. Though their impact on atmospheric composition remains minimal for several hundred million years, These early photosynthetic bacteria operate in shallow marine environments where sunlight penetrates the water column, using carbon dioxide and water to produce organic compounds while releasing molecular oxygen as a byproduct. The oxygen initially dissolves in seawater, where it begins its slow chemical assault on the reduced iron and sulfur compounds that dominate early ocean chemistry. The photosynthetic reaction operates through a complex sequence of biochemical steps that split water molecules using solar energy captured by chlorophyll and other light-harvesting pigments. The process requires sophisticated molecular machinery, including photosystem II, one of the most complex enzyme systems known, capable of extracting electrons from water at thermodynamic potentials that would be lethal to most biological molecules. The evolution of this biochemical system represents one of the most significant innovations in the history of life on Earth. Oxygen toxicity affects early life forms through the formation of reactive oxygen species that damage cellular components, including DNA, proteins, and lipid membranes. Most archaean organisms lack the biochemical defenses against oxidative damage that protect modern aerobic life, making them vulnerable to oxygen concentrations that would be trivial by modern standards. The gradual accumulation of oxygen in seawater creates expanding dead zones where anaerobic organisms cannot survive, forcing evolutionary adaptation or extinction. The initial oxygen production remains buffered by the enormous reservoir of reduced iron dissolved in seawater, which reacts with oxygen to form iron oxide precipitates. This chemical buffering delays atmospheric oxygen accumulation for hundreds of millions of years while consuming virtually all biologically produced oxygen through abiotic chemical reactions. The iron-oxygen reaction creates distinctive mineral deposits that serve as geological markers for the onset of oxygenic photosynthesis. Stromatolites, layered structures built by cyanobacterial mats, provide direct evidence for early photosynthetic communities and their environmental impact. These distinctive formations preserve microscopic textures that reveal the presence of oxygen-producing bacteria in shallow marine environments. The stromatolites also preserve chemical signatures, including sulfur isotope ratios that record the changing redox conditions in early marine ecosystems, as oxygen production gradually overwhelms the ocean's reducing capacity. Scientists study early oxygen production through the analysis of sulfur isotopes in ancient sedimentary rocks. The sulfur isotope signatures preserve information about atmospheric chemistry because sulfur dioxide in the atmosphere undergoes mass-independent fractionation that creates distinctive isotopic patterns. The disappearance of these mass-independent signatures from the geological record marks the transition to an oxygenated atmosphere that prevents the photochemical reactions responsible for the unusual isotopic fractionation. Yet significant uncertainties remain about the timing and mechanisms of early oxygenation. How did cyanobacteria evolve the complex biochemistry required for water-splitting photosynthesis? What environmental factors controlled the initial spread of oxygen-producing organisms? The sparse fossil record from this period preserves only indirect evidence of early life, requiring creative interpretation of chemical and isotopic signatures to reconstruct biological processes operating billions of years ago. The ecological impact of early oxygen production extends far beyond direct toxicity to anaerobic organisms. Oxygen reacts with methane in the atmosphere, destroying this important greenhouse gas and potentially triggering climate cooling that leads to global glaciation events. The oxidation of atmospheric methane also produces carbon dioxide and water vapor, altering atmospheric composition and climate dynamics in complex ways that influence biological productivity and evolution. Biogeochemical cycling of nutrients undergoes fundamental changes as oxygen accumulation affects the solubility and transport of essential elements. Iron precipitation removes this essential micronutrient from surface waters, potentially limiting biological productivity despite abundant sunlight and carbon dioxide. Phosphorus cycling changes as iron oxides sequester phosphate minerals, altering the nutrient ratios available to marine organisms and influencing evolutionary adaptations to nutrient limitation. The development of cellular defenses against oxygen toxicity drives major innovations in biochemistry and cellular organization. Antioxidant enzyme systems evolve to neutralize harmful reactive oxygen species before they damage cellular components. Compartmentalization of cellular functions protects sensitive biochemical processes from oxidative damage. These defensive innovations eventually enable organisms to exploit oxygen for aerobic respiration, turning the former poison into the foundation for high-energy metabolism. Horizontal gene transfer accelerates evolutionary responses to oxygen stress, as organisms share genetic innovations that provide protection against oxidative damage. Genes. Encoding antioxidant enzymes, oxygen-tolerant metabolic pathways, and cellular repair mechanisms spread rapidly through microbial communities facing oxygen exposure. This genetic sharing creates a form of evolutionary cooperation that enhances survival during environmental crisis. The geographic spread of oxygenated water creates complex environmental gradients that influence biological community structure and evolutionary processes. Shallow marine environments experience the highest oxygen concentrations, while deep ocean basins remain anoxic for hundreds of millions of years longer. These spatial gradients in oxygen availability create diverse ecological niches that support different metabolic strategies and evolutionary innovations. Like a slow-motion ecological catastrophe unfolding over hundreds of millions of years, the Great Oxygenation Event transforms Earth's surface chemistry and eliminates most existing life forms while creating opportunities for new evolutionary innovations. Only took 300 million years to completely restructure planetary biogeochemistry. The cyanobacteria continue their patient work, splitting water molecules and releasing oxygen with the steady persistence that will eventually make possible the complex life forms that will inherit an oxygenated planet. In their microscopic photosynthetic machinery lies encoded the future of all aerobic life on Earth. Banded iron's quiet testament lies written in stone across the world's most ancient continental fragments, where alternating layers of iron-rich and iron-poor minerals record the ocean's struggle with the new oxygen being pumped into its depths by countless generations of cyanobacteria. These distinctive sedimentary formations, with their rhythmic stripes of red, black, and silver, preserve a billion-year archive of early Earth's chemical transformation as an entire planet learned to accommodate the toxic waste product of photosynthesis. The formation mechanism of banded iron operates through seasonal or longer-term cycles that control iron precipitation in early marine environments. During periods of low oxygen production, dissolved iron accumulates in seawater as ferrous ions that impart a reddish-brown coloration to the ocean. When cyanobacterial activity increases, either seasonally or through ecological expansion, oxygen concentrations rise sufficiently to precipitate iron as magnetite, hematite, or other iron oxide minerals that settle to the seafloor as thin layers. The mineralogy of banded iron formations reveals complex chemical conditions during precipitation. Magnetite layers form under moderately reducing conditions where some oxygen is present, but not enough to fully oxidize all available iron. Hematite bands precipitate during periods of higher oxygen availability when more complete oxidation occurs. Siderite layers develop under strongly reducing conditions where carbon dioxide reacts with iron to form iron carbonate minerals. These mineral associations create a detailed record of redox fluctuations in early ocean chemistry. Silica precipitation accompanies iron deposition through mechanisms that remain incompletely understood. The silica likely derives from weathering of continental rocks and hydrothermal activity, accumulating in seawater until it reaches saturation and precipitates as chert layers between iron-rich bands. Some researchers propose that silica precipitation was mediated by early microorganisms, though direct evidence for biological involvement remains elusive. The alternating iron and silica layers create the characteristic banded appearance that gives these formations their name. The global distribution of banded iron formations indicates widespread similar ocean chemistry conditions across different ocean basins during the Archean and Paleoproterozoic eras. These formations occur on every continent, suggesting that the iron precipitation process operated on a planetary scale rather than in isolated basins. The synchronous timing of iron formation worldwide provides evidence for global ocean circulation that mixed dissolved iron and oxygen across continental margins. Trace element chemistry in banded iron formations preserves information about early ocean composition and biological activity. Rare earth element patterns reflect seawater chemistry influenced by hydrothermal input and continental weathering. Sulfur isotope signatures record bacterial sulfate reduction and other metabolic processes operating in early marine environments. These geochemical proxies allow reconstruction of ocean chemistry and biological activity from time periods when direct fossil evidence remains scarce. Scientists study banded iron formation chemistry through high-resolution sampling that reveals sub-millimeter variations in mineral composition and trace element concentrations. These detailed analyses reveal complex depositional processes, including multiple phases of mineral precipitation, post-depositional alteration, and metamorphic modification. The preservation of primary chemical signatures requires careful evaluation of subsequent geological processes that may have modified original compositions. Yet fundamental questions persist about banded iron formation genesis and its relationship to early biological activity. Why did iron precipitation occur in such regular cyclic patterns over millions of years? What role did early microbial communities play in modulating iron and silica precipitation? The absence of modern analogues for banded iron formation makes it difficult to test proposed formation mechanisms through direct observation of active processes. The cessation of banded iron formation around 1.8 billion years ago marks a fundamental transition in Earth's surface chemistry as atmospheric oxygen levels rise sufficiently to prevent large-scale iron accumulation in seawater. This transition represents one of the most dramatic changes in Earth's surface environment, permanently altering ocean chemistry and creating new opportunities for biological evolution. The end of iron formation coincides with the first appearance of eukaryotic cells and other evolutionary innovations enabled by higher oxygen availability. Metamorphic alteration of banded iron formations creates some of the world's highest-grade iron ore deposits through processes that concentrate iron minerals and remove silica. Regional metamorphism recrystallizes the original fine-grained minerals into coarser-grained assemblages while preserving the original banded structure. Weathering of metamorphosed iron formations produces supergene enrichment that further concentrates iron content and improves ore quality for industrial extraction. The economic importance of banded iron formations as iron ore sources connects modern industrial civilization directly to early Earth's oxygenation events. Most of the world's iron ore reserves derive from Precambrian banded iron formations, making modern steel production dependent on geological processes that operated billions of years ago. This connection between deep-time geology and contemporary technology illustrates the long-term consequences of early biological innovations. Paleomagnetic studies of banded iron formations provide information about ancient magnetic field behavior and continental positions during early Earth history. The magnetic minerals in iron formations preserve records of magnetic field direction and intensity that allow reconstruction of apparent polar wanderpaths and continental drift over geological time. These paleomagnetic data contribute to understanding of early plate tectonic processes and continental assembly. The regular cyclicity observed in many banded iron formations suggests astronomical forcing of depositional processes through orbital variations that control climate and oceanic circulation. Spectral analysis of band thickness variations reveals periodicities that may correspond to Milankovitch cycles, though the interpretation of these patterns remains controversial due to the difficulty of establishing precise age controls for Precambrian rocks. Like pages in Earth's oldest library, the bands of iron and silica preserve a readable record of the planet's first great environmental crisis and recovery. Only took 1 billion years to write this mineral manuscript. The formations continue to weather and erode today, releasing their ancient iron back to modern rivers and oceans where it supports contemporary biological productivity. In the rhythmic layers of rust and quartz lies encoded both the memory of Earth's toxic transition and the foundation for the oxygenated world that makes complex life possible. When water learned to breathe. Oxygen saturation reaches a tipping point that fundamentally alters the ocean's chemistry forever, transforming the ancient iron-rich seas into something approaching modern marine conditions. This critical threshold occurs not gradually, but as a cascade of chemical changes that propagate through the global ocean system over geological timescales, measured in millions rather than billions of years. The transition marks the moment when Earth's surface chemistry crosses an irreversible boundary into an oxygenated world. The oxygen saturation process operates through complex feedback mechanisms between biological production, chemical consumption, and atmospheric exchange. As cyanobacterial populations expand across shallow marine environments, their collective oxygen output eventually exceeds the ocean's capacity to consume oxygen through reaction with dissolved iron and other reduced compounds. This excess oxygen begins to accumulate in surface waters, creating the first permanently oxygenated marine environments in Earth's history. Dissolved oxygen concentrations in early oxygenated seawater remain far below modern levels, perhaps only a few % of current atmospheric saturation. Yet even these low concentrations prove sufficient to drive massive changes in ocean chemistry as oxygen reacts with previously stable reduced compounds. Sulfide minerals oxidize to sulfate, creating more acidic conditions that accelerate rock weathering. Organic matter undergoes more complete decomposition in the presence of oxygen, altering carbon cycling and nutrient availability. The vertical structure of ocean oxygenation creates distinct chemical zones that influence biological community composition and mineral precipitation patterns. Surface waters achieve oxygen saturation first, while deep ocean basins remain anoxic for hundreds of millions of years longer. This chemical stratification creates sharp redox boundaries that concentrate certain chemical reactions and biological processes into narrow depth intervals where oxidized and reduced waters meet. Seasonal variations in oxygen production create temporal fluctuations in redox conditions that influence mineral precipitation and biological activity. During periods of peak photosynthetic activity, oxygen concentrations rise sufficiently to precipitate iron oxides and other oxidized minerals. When photosynthetic activity decreases, oxygen levels drop and reducing conditions return, allowing dissolution of previously precipitated minerals. These oscillations create complex sedimentary records that preserve evidence of early oxygenation dynamics. The evolution of aerobic respiration fundamentally changes marine ecosystem energetics as organisms learn to exploit oxygen for high-energy metabolism. Aerobic respiration yields far more energy per unit of organic matter than anaerobic metabolic pathways, enabling larger cell sizes, more complex cellular organization, and higher activity levels. This metabolic revolution creates new ecological opportunities and drives evolutionary innovations that will eventually lead to multicellular life. Scientists study early ocean oxygenation through multiple geochemical proxies that record redox conditions in ancient marine environments. Chromium isotopes reflect the availability of oxygen for chromium oxidation reactions. Molybdenum concentrations indicate the extent of sulfidic water masses in ocean basins. Iron speciation in sedimentary rocks records local redox conditions during deposition. These proxies often disagree, reflecting the complex spatial and temporal heterogeneity of early oxygenation. Yet significant uncertainties remain about the mechanisms and timing of ocean oxygenation. How did oxygen concentrations remain stable once they began to accumulate? What role did changing continental configurations play in ocean circulation and oxygenation patterns? The sparse and often contradictory geochemical evidence from this period makes it difficult to reconstruct detailed histories of oxygenation in different ocean basins. The biological response to ocean oxygenation includes both extinction of oxygen-sensitive organisms and evolutionary innovation of oxygen-tolerant metabolisms. Many anaerobic bacteria and archaea retreat to deep ocean environments or sedimentary habitats where reducing conditions persist. Other organisms evolve biochemical defenses against oxygen toxicity, including antioxidant enzyme systems and cellular repair mechanisms that protect against oxidative damage. Biogeochemical cycling of nutrients undergoes fundamental reorganization as oxygen availability affects the solubility and transport of essential elements. Phosphorus cycling changes as iron oxides precipitate and sequester phosphate minerals in sediments. Nitrogen cycling develops new pathways as nitrification and denitrification reactions become possible under oxygenated conditions. These changes in nutrient availability influence biological productivity and community structure throughout marine ecosystems. The geographic pattern of ocean oxygenation reflects complex interactions between biological oxygen production, physical circulation, and chemical consumption rates. Shallow marine environments on continental shelves experience oxygenation first due to their proximity to photosynthetic communities and efficient atmospheric gas exchange. Deep ocean basins and restricted marine environments remain anoxic longer due to limited circulation and continued oxygen consumption by organic matter decomposition. Atmospheric oxygen levels rise in parallel with ocean oxygenation, though the two reservoirs equilibrate slowly due to the large differences in their size and circulation rates. The atmosphere's oxygen content increases from essentially 0 to perhaps 1% of modern levels during the initial oxygenation event. This atmospheric oxygen provides a buffer against short-term fluctuations in biological oxygen production and enables oxygen transport to marine environments distant from photosynthetic communities. The carbonate chemistry of seawater changes dramatically as oxygen availability affects the precipitation and dissolution of calcium carbonate minerals. Oxygenated conditions favor the precipitation of calcium carbonate shells and skeletons, creating new opportunities for biomineralization. The pH buffering provided by carbonate chemistry helps stabilize ocean conditions during the transition to oxygenated conditions. Hydrothermal systems adapt to oxygenated ocean conditions through changes in mineral precipitation and microbial community composition. Oxidized metals like iron and copper precipitate more readily in oxygenated seawater, altering the chemistry of hydrothermal deposits. Chemosynthetic bacterial communities that depend on reduced chemical compounds must adapt to lower concentrations of their preferred substrates in increasingly oxygenated bottom waters, like learning to breathe after a lifetime underwater. The ocean's adaptation to oxygen represents a fundamental physiological transformation that enables entirely new forms of chemical and biological complexity. Only took 200 million years for the ocean to master this new respiratory skill. The process continues today as marine organisms regulate oxygen concentrations through photosynthesis and respiration, maintaining the delicate chemical balance that sustains modern marine ecosystems. In every breath of oxygen dissolved in seawater lies the legacy of this ancient transformation. When water first learned to hold and transport the life-giving gas that makes aerobic existence possible, the deep current's ancient dance begins its slow, planetary-scale mixing as thermohaline circulation establishes the first global conveyor belt that will transport heat, nutrients, and dissolved gases across ocean basins for the remainder of Earth's history. This massive circulation system operates through density differences created by temperature and salinity variations, driving water masses on journeys that span thousands of kilometers and hundreds of years. The currents move with the patient persistence of geological time, reshaping ocean chemistry one molecule at a time. Thermohaline circulation on early Earth operates under conditions dramatically different from modern ocean dynamics. The absence of polar ice caps eliminates the source of cold, dense water that drives much of today's deep ocean circulation. Instead, salinity variations created by evaporation in restricted basins and dilution by rainfall and river input provide the primary density contrasts that generate circulation. The early ocean's higher salinity and temperature create weaker density gradients that drive slower, more diffuse circulation patterns. The formation of deep water masses begins in regions where surface waters become sufficiently dense to sink to the ocean floor. In the early ocean, these formation regions likely occur in shallow, restricted basins where evaporation concentrates dissolved salts and increases water density. The sinking water carries with it the chemical signature of surface conditions, including dissolved oxygen from photosynthetic activity and trace elements from continental weathering and hydrothermal input. Ocean basin geometry plays a critical role in determining circulation patterns, with the scattered continental fragments of early Earth creating a complex network of seaways and restricted basins. The small size and irregular distribution of early continents prevent the development of large-scale current systems like the modern Gulf Stream or Antarctic Circumpolar Current. Instead, circulation occurs through smaller, regional gyres that transport water masses between continental fragments and volcanic archipelagos. The chemistry of early deep water differs markedly from modern conditions due to the absence of biological productivity in deep ocean environments. Without the rain of organic matter that characterizes modern oceans, deep waters remain nutrient-poor and chemically stable over long residence times. The lack of oxygen consumption through organic matter decomposition allows oxygenated deep waters to persist longer, though overall, oxygen levels remain far below modern concentrations. Mixing processes in early ocean circulation operate more slowly than modern systems due to the weaker density gradients and simpler basin geometry. The vertical mixing between surface and deep waters occurs primarily through diffusion and weak convective processes rather than the vigorous overturning circulation that characterizes modern oceans. This slower mixing allows chemical gradients to persist for longer periods, creating stable chemical stratification in some ocean regions. Scientists study ancient ocean circulation through the analysis of carbon and strontium isotopes in sedimentary rocks that preserve evidence of water mass chemistry and mixing patterns. Carbon isotope gradients between surface and deep ocean environments indicate the strength of vertical mixing and organic matter cycling. Strontium isotopes reflect the relative contributions of continental weathering and hydrothermal input to seawater chemistry, both of which depend on circulation patterns and residence times. Yet, fundamental uncertainties remain about early ocean circulation dynamics and their influence on climate and chemistry. How did the absence of significant topographic barriers affect current patterns and heat transport? What role did tidal mixing play in driving circulation in the shallow, restricted basins of early Earth? The lack of detailed bathymetric information for early ocean basins makes it difficult to model circulation patterns with confidence. The heat transport capacity of early ocean circulation influences global climate patterns through redistribution of thermal energy from equatorial to polar regions. The weaker circulation systems of early Earth provide less efficient heat transport than modern currents, potentially contributing to larger temperature gradients between low and high latitudes. This reduced heat transport may have influenced the development of ice ages and other climate variations during early Earth history. Nutrient transport by ocean circulation affects biological productivity patterns and ecosystem development in early marine environments. The circulation system redistributes essential elements like phosphorus, nitrogen, and trace metals from regions of high input to areas where they can support biological activity. The slower circulation of early oceans may have created more pronounced regional variations in nutrient availability and biological productivity. The interaction between ocean circulation and atmospheric circulation creates coupled climate dynamics that influence both marine and terrestrial environments. Ocean currents transport heat and moisture that affect atmospheric temperature and humidity patterns. Atmospheric circulation drives surface ocean currents through wind stress and influences evaporation and precipitation patterns that control ocean salinity. These coupled interactions operate over multiple timescales from seasonal to geological. Deep ocean ventilation through thermohaline circulation provides the primary mechanism for delivering oxygen to abyssal environments where photosynthesis cannot occur. The ventilation timescales determine how long deep waters remain isolated from surface processes and how efficiently dissolved gases and nutrients mix throughout the ocean volume. Early ocean ventilation likely operates much slower than modern systems, allowing chemical gradients to develop and persist in deep water masses. The chemical weathering products transported by ocean circulation create regional variations in seawater composition that influence mineral precipitation and biological activity. Circulation patterns determine which weathering sources contribute to different ocean regions, creating geographic variations in trace element concentrations and isotopic compositions. These chemical differences may have influenced early biological evolution by creating diverse chemical environments that selected for different metabolic strategies. Paleoceanographic reconstructions using geochemical proxies reveal evidence for major changes in circulation patterns during early Earth history, including periods of enhanced mixing and intervals of chemical stratification. These circulation changes correlate with major geological events, including volcanic episodes, continental assembly, and early glaciation events. The circulation system responds to external forcing while also influencing surface conditions through heat and chemical transport, like the slow heartbeat of a sleeping planet. Thermohaline circulation establishes the rhythm of chemical and thermal exchange that will sustain ocean ecosystems for billions of years to come. only took 500 million years to establish the basic circulation patterns that continue today. The ancient currents flow beneath modern seas, their paths modified by changing continental configurations, but their fundamental physics unchanged since the early ocean first learned to mix its chemical contents on a global scale. In every drop of deep ocean water lies the memory of journeys begun billions of years ago, when circulation first connected the scattered seas of early Earth into a single planetary ocean system. Snowball Earth's frozen rivers lock most of the planet's water in ice for millions of years, as global glaciation transforms Earth into a crystalline sphere reflecting sunlight back to space with the efficiency of a cosmic mirror. The rivers that once carried dissolved continents to the sea now freeze solid from source to mouth, their flow suspended in geological time, while ice sheets kilometers thick advance across every landmass and ocean surface. This planetary refrigeration operates through runaway climate feedback that transforms liquid water into a solid archive of Earth's most extreme climate state. The onset of global glaciation begins with subtle changes in atmospheric chemistry and continental configuration that tip Earth's delicate energy balance toward cooling. Reduced volcanic outgassing decreases atmospheric carbon dioxide concentrations below the threshold necessary to maintain liquid water under the faint young sun's reduced luminosity. The weathering of newly exposed continental rocks consumes additional carbon dioxide, accelerating the cooling process through biological and chemical feedback mechanisms. Ice albedo feedback amplifies initial cooling as expanding ice sheets reflect increasing amounts of solar radiation back to space. The highly reflective ice surface absorbs far less solar energy than dark ocean water or bare rock, creating a positive feedback loop that drives further cooling and ice expansion. Once ice coverage exceeds a critical threshold, the feedback becomes unstoppable, plunging the planet into complete glaciation within a few thousand years. The thickness of snowball Earth ice sheets reaches several kilometers in continental regions and perhaps hundreds of meters over ocean basins. These massive ice accumulations lock up enormous volumes of water, lowering global sea level by hundreds of meters and exposing continental shelves that remain frozen and dry throughout the glaciation. The ice sheets flow under their own weight, carving deep valleys and transporting enormous volumes of rock debris across the frozen landscape. Atmospheric circulation during snowball Earth operates under conditions unlike any experienced in Earth's subsequent history. The temperature difference between equatorial and polar regions essentially disappears, eliminating the thermal gradients that drive modern weather systems. Atmospheric pressure drops significantly as water vapor freezes out of the atmosphere, creating thin, dry air with minimal greenhouse capacity. Winds blow across the ice surface with little moisture content, creating a hyper-arid global desert of ice. Volcanic activity continues beneath the ice sheets, creating localized melting and unique volcanic ice interactions that produce distinctive geological formations. Subglacial volcanic eruptions create pillow lavas and hyaloclastite deposits formed through rapid cooling in contact with ice and meltwater. Geothermal heat from volcanic regions creates temporary pockets of liquid water that may serve as refugia for surviving microbial communities during the global freeze. Ocean circulation beneath the global ice cover operates through a combination of geothermal heating and tidal forces that maintain limited water movement in the deepest ocean basins. The ice-covered ocean surface prevents atmospheric gas exchange, creating isolated water masses with chemical compositions that evolve independently over millions of years. Brine pockets within sea ice concentrate, dissolve salts, and may provide chemical microenvironments that support minimal biological activity. Scientists study snowball Earth events through the analysis of glacial deposits called tillites that preserve evidence of ice sheet activity in tropical latitudes. These distinctive sedimentary rocks contain angular rock fragments and striated stones that indicate transport by glacier ice. The global distribution of tillites of similar age provides evidence that glaciation affected all latitudes simultaneously, supporting the snowball Earth hypothesis over alternative explanations of regional glaciation. Yet significant controversies remain about snowball Earth dynamics and the survival of life during global glaciation. How did atmospheric and oceanic circulation operate under completely ice-covered conditions? What mechanisms allowed life to persist through millions of years of global freezing? The extreme conditions of snowball Earth have no modern analogues, making it difficult to test proposed mechanisms through direct observation or laboratory experiments. The termination of snowball Earth requires massive volcanic carbon dioxide emissions that gradually accumulate in the ice-covered atmosphere over millions of years. Without liquid water to consume carbon dioxide through weathering reactions, volcanic outgassing slowly increases atmospheric greenhouse gas concentrations until they reach levels sufficient to begin melting the global ice cover. The deglaciation process occurs rapidly once it begins, with runaway greenhouse warming reversing the ice albedo feedback. Biological survival during snowball Earth likely occurs in specialized refugia, including hydrothermal vents, geothermally heated pools, and chemical microenvironments within sea ice and glacial meltwater. Microbial communities may persist in these isolated habitats for millions of years, maintaining genetic diversity and metabolic capabilities that enable rapid recolonization when liquid water returns. The survival mechanisms remain poorly understood due to the lack of direct fossil evidence from snowball Earth periods. Geochemical evidence for snowball Earth includes unusual carbon isotope signatures that indicate complete shutdown of biological productivity and carbon cycling. The carbon isotope ratios in rocks deposited during glaciation show extreme values that suggest minimal organic carbon production and unusual carbonate precipitation processes. These isotopic anomalies provide independent evidence for the extreme environmental conditions proposed by snowball Earth models. The impact of snowball Earth on evolutionary processes includes both mass extinction of cold-sensitive organisms and evolutionary innovation driven by extreme environmental stress. The severe bottleneck imposed by global glaciation may have accelerated evolutionary change by reducing population sizes and increasing selection pressure. Some researchers propose that snowball Earth events triggered major evolutionary innovations, including the development of multicellularity and complex cell structures. Continental weathering essentially ceases during snowball Earth as chemical reactions slow dramatically under sub-freezing conditions and liquid water becomes unavailable for rock-water interactions. This shutdown of the weathering cycle allows atmospheric carbon dioxide to accumulate from volcanic sources without consumption, eventually enabling the greenhouse warming that terminates the glaciation. The cessation of weathering also affects ocean chemistry by eliminating the supply of dissolved nutrients from continental sources. The sedimentary record of snowball Earth termination preserves evidence of rapid environmental change as global ice melting creates massive floods and extreme weathering conditions. Cap carbonates deposited immediately after glaciation show unusual chemical compositions that reflect the rapid return of liquid water and accelerated rock weathering under high atmospheric carbon dioxide concentrations. These distinctive rock formations provide markers for identifying snowball Earth events in the geological record, like a planetary hibernation that preserves Earth's essential processes in suspended animation. Snowball Earth demonstrates the resilience of life and the power of feedback systems to drive extreme climate change. Only took 10 million years to freeze the entire planet solid. The Ice Age ends as dramatically as it began, with runaway greenhouse warming that melts the global ice cover and unleashes torrents of meltwater that carve new river channels and fill ocean basins with the accumulated chemical products of millions of years of volcanic outgassing. In the memory of frozen rivers lies encoded both the fragility and persistence of liquid water on a dynamic planet. The thaw and ocean's rebirth unfold with geological patience as volcanic carbon dioxide slowly melts the frozen world back to life, molecule by molecule, degree by degree, until liquid water once again flows across a planet that has forgotten the touch of rain. The atmosphere thickens with volcanic exhalations accumulated over millions of years beneath the global ice cover, creating greenhouse conditions intense enough to overcome the reflective power of planetary ice and initiate the great melting that will restore Earth's hydrological cycle. Carbon dioxide concentrations rise to levels hundreds of times higher than modern atmospheric content as volcanic outgassing continues unabated, while the frozen planet provides no weathering sink to consume the accumulating greenhouse gases. This extreme atmospheric composition creates surface pressures and greenhouse warming unlike any other period in Earth's history. The dense carbon dioxide atmosphere absorbs and re-radiates thermal energy with such efficiency that surface temperatures begin to rise even beneath the global ice cover. The initial melting begins at the base of ice sheets, where geothermal heat from volcanic activity and radioactive decay creates thin films of liquid water between ice and rock. These basal melt layers lubricate ice flow and create subglacial drainage systems that transport water and dissolved minerals beneath the ice cover. The hidden hydrology of Snowball Earth operates in darkness, carrying the chemical products of rock weathering through networks of tunnels and caverns carved in the ice sheet base. Atmospheric warming proceeds slowly, at first, as the massive thermal inertia of global ice cover resists temperature change. The ice surface remains highly reflective, bouncing most incoming solar radiation back to space despite the thickening atmosphere. Yet, the greenhouse effect operates continuously, trapping thermal radiation from both solar heating and geothermal sources. Eventually, atmospheric temperatures rise above the freezing point, and the first liquid water appears on the planetary surface in over 10 million years. The transition from frozen to liquid water accelerates rapidly once surface melting begins, as dark meltwater pools absorb solar radiation far more efficiently than reflective ice. This albedo feedback reverses the ice albedo feedback that created Snowball Earth, driving runaway warming that melts ice sheets at rates measured in meters per year. The planetary ice cover disappears within a few thousand years, transforming Earth from a frozen snowball to a superheated greenhouse world, almost instantaneously in geological terms. Meltwater floods of unprecedented scale carve new river channels and fill ocean basins as the equivalent of several kilometers of ice converts to liquid water within millennia. These megafloods transport enormous volumes of sediment and dissolved minerals that have accumulated in and beneath ice sheets for millions of years. The flood deposits preserve evidence of the catastrophic deglaciation in distinctive sedimentary formations that cap the glacial deposits worldwide. Ocean chemistry during the immediate post-snowball period differs dramatically from both pre-glacial and modern seawater due to the extreme atmospheric conditions and rapid weathering under superheated greenhouse climate. The high carbon dioxide concentrations create strongly acidic conditions that accelerate chemical weathering of exposed continental rocks. Rivers deliver massive chemical loads to the newly liquid oceans, creating alkaline conditions that neutralize atmospheric acidity through carbonate precipitation. The cap carbonates that form immediately after Snowball Earth represent some of the most unusual carbonate rocks in the geological record, with chemical compositions that reflect the extreme environmental conditions during deglaciation. These distinctive limestone formations precipitate directly from seawater with unusual carbon and oxygen isotope signatures that record the rapid changes in atmospheric and oceanic chemistry. The cap carbonates provide chronological markers that allow correlation of snowball Earth events worldwide. Scientists study snowball Earth termination through multiple lines of evidence, including paleomagnetism, geochemistry, and sedimentology, that together constrain the timing and mechanisms of deglaciation. Paleomagnetic directions in cap carbonates indicate rapid changes in continental positions during and after glaciation. Geochemical proxies record extreme values of temperature, pH, and atmospheric composition. Sedimentological features preserve evidence of catastrophic flooding and rapid environmental change. Yet fundamental questions remain about deglaciation dynamics and their effects on life and climate systems. How did atmospheric circulation re-establish after millions of years of frozen conditions? What role did ocean chemistry play in buffering the extreme greenhouse conditions during deglaciation? The unique conditions of snowball Earth termination have no modern analogues, making it difficult to test proposed mechanisms through laboratory experiments or numerical models. Biological recovery after snowball Earth proceeds through rapid recolonization from refugia and evolutionary radiation into empty ecological niches created by mass extinction during glaciation. Microbial communities expand from hydrothermal vents, subglacial environments, and other refugia where life persisted through the global freeze. The extreme environmental conditions during deglaciation may have accelerated evolutionary processes through intense selection pressure and genetic bottlenecks. Weathering rates during the post-snowball greenhouse period exceed modern rates by orders of magnitude due to the combination of high atmospheric carbon dioxide, elevated temperatures, and abundant liquid water. This enhanced weathering rapidly consumes excess atmospheric carbon dioxide, moderating the extreme greenhouse conditions within a few million years. The weathering products accumulate as thick sedimentary sequences that preserve records of the intense chemical activity during climate recovery. Hydrothermal activity increases during deglaciation as ice-loading changes affect crustal stresses and volcanic activity patterns. The removal of massive ice sheets triggers isostatic rebound that influences magma generation and eruption rates. Enhanced hydrothermal circulation delivers dissolved metals and other chemical components to the recovering ocean system, contributing to the unusual chemistry of early post-glacial seawater. Ocean circulation re-establishes gradually as thermal gradients develop between equatorial and polar regions for the first time in millions of years. The return of normal temperature gradients drives atmospheric circulation that generates wind patterns and ocean currents. The development of thermohaline circulation helps distribute heat and chemicals throughout the ocean system, moderating regional climate variations and supporting biological productivity. Climate stabilization after snowball Earth requires hundreds of millions of years as feedback systems gradually balance atmospheric composition, ocean chemistry, and biological activity. The carbon cycle slowly returns to steady-state conditions as weathering rates decline and volcanic outgassing decreases. Continental positions continue to evolve through plate tectonics, influencing climate patterns and ocean circulation throughout the recovery period. Like a planetary resurrection from the deepest possible winter, the thaw transforms Earth from crystalline death to liquid life with the power of accumulated volcanic breath and the patience of geological time. Only took a few million years to completely melt away 10 million years of ice. The reborn ocean spreads across the planetary surface, its chemistry exotic and its temperature elevated. but carrying within its molecular structure the potential for biological renaissance and the chemical complexity that will enable evolutionary innovations yet unimagined in the simple microbial world that emerges from Snowball Earth's icy embrace. Complex chemistry's quiet dawn emerges from the post-Snowball ocean conditions as new chemical equilibria and mineral assemblages create opportunities for more sophisticated molecular interactions than Earth's surface has ever supported. The extreme greenhouse warming that follows global deglaciation drives intense weathering that delivers unprecedented concentrations of dissolved elements to seawater, while the gradual return of atmospheric oxygen creates redox gradients that enable novel chemical reactions and metabolic pathways. The chemical complexity of post-Snowball seawater exceeds that of any previous ocean due to the combination of enhanced continental weathering under superheated greenhouse conditions and the cessation of normal chemical cycling during millions of years of global glaciation. Rivers deliver massive loads of dissolved silica, aluminum, iron, and trace metals that accumulate in seawater concentrations far above normal solubility limits. These supersaturated solutions create metastable chemical conditions that allow unusual mineral precipitation and complex solution chemistry. Redox chemistry becomes increasingly sophisticated as atmospheric oxygen gradually returns to pre-glacial levels and begins to interact with the metal-rich seawater chemistry created by enhanced weathering. The oxygen creates sharp chemical gradients between oxidized surface waters and reduced deep waters, establishing redox boundaries that concentrate chemical reactions and create opportunities for chemosynthetic metabolism. These redox interfaces become centers of chemical innovation where new mineral assemblages and metabolic pathways develop. The pH buffering capacity of post-Snowball seawater increases dramatically due to high concentrations of dissolved carbonate and silicate minerals that neutralize the acidic conditions created by elevated atmospheric carbon dioxide. This enhanced buffering allows seawater pH to remain within ranges compatible with biological activity despite extreme atmospheric compositions. The buffering reactions create complex carbonate chemistry that influences mineral solubility and biological calcification processes. Trace element chemistry develops new complexity as enhanced weathering delivers unusual concentrations of rare earth elements, transition metals, and other trace components to seawater. These elements participate in complex coordination chemistry with organic molecules and create opportunities for new enzymatic processes and metabolic innovations. The availability of diverse trace elements may have enabled the evolution of more sophisticated biochemical machinery, including advanced metalloenzymes and electron transport systems. Organic geochemistry begins to develop as surviving microbial communities expand into the recovering ocean system and begin producing more diverse and complex organic molecules. The extreme environmental conditions during and after Snowball Earth may have selected for organisms capable of synthesizing novel organic compounds that provide protection against environmental stress or enable exploitation of new chemical resources. These biochemical innovations create the foundation for more complex organic chemistry. Scientists study post-Snowball chemical evolution through analysis of molecular fossils and biomarker compounds preserved in sedimentary rocks deposited during the recovery period. These organic molecules provide evidence for the types of organisms present and their metabolic capabilities. The biomarker signatures show increasing molecular complexity over time as ecosystems recover and evolve new biochemical capabilities in response to changing environmental conditions. Yet, significant uncertainties remain about the mechanisms and timing of chemical evolution during Earth's recovery from global glaciation. How did complex chemical systems develop stability under the extreme and rapidly changing conditions of the post-snowball environment? What role did mineral surfaces play in catalyzing new chemical reactions and stabilizing complex molecules? The sparse preservation of organic materials from this period limits direct evidence for early chemical evolution. Biomineralization processes undergo major innovations as organisms develop new mechanisms for precipitating calcium carbonate, silica, and phosphate minerals under the unusual chemical conditions of post-snowball seawater. The high concentrations of dissolved minerals provide abundant raw materials for biological mineral formation, while the complex solution chemistry creates new opportunities for controlling mineral nucleation and growth. These innovations in biomineralization may have enabled the first development of hard skeletal structures. Clay mineral formation accelerates under the intense weathering conditions that follow snowball Earth, creating new surface environments for chemical reactions and possibly biological activity. Clay minerals provide catalytic surfaces that can concentrate organic molecules and facilitate polymerization reactions that create larger, more complex molecular structures. The expanding clay mineral environments may have served as primitive laboratories for chemical evolution and early biochemical innovations. The phosphorus cycle undergoes fundamental changes as enhanced weathering delivers massive amounts of phosphate minerals to the ocean system. While the changing redox conditions affect phosphorus solubility and bioavailability, phosphorus serves as an essential component of nucleic acids, cell membranes, and energy storage molecules, making its increased availability potentially crucial for supporting more complex cellular biochemistry and larger organism size. Sulfur chemistry develops new complexity as atmospheric oxygen interacts with sulfur compounds from enhanced weathering and continued volcanic outgassing. The sulfur cycle creates opportunities for new metabolic pathways, including sulfate reduction and sulfur oxidation, that provide energy sources for chemosynthetic organisms. Complex sulfur chemistry also influences the precipitation of metal sulfide minerals that may serve as catalysts for organic synthesis reactions. Iron chemistry transitions from the simple ferrous-ferric systems that dominated earlier Earth history to more complex ion coordination chemistry involving organic ligands and mixed valence mineral phases. The availability of oxygen for ion oxidation creates new ion mineral phases with different catalytic properties and surface chemistries. These iron phases may have played important roles in early biochemical evolution by providing catalytic surfaces for metabolic reactions. Silicon chemistry expands beyond simple silicate mineral formation to include more complex silica phases and possibly early biosilicification processes. The high dissolved silica concentrations in post-snowball seawater create opportunities for organisms to incorporate silica into biological structures. Some researchers propose that early silicon biochemistry may have provided templates or scaffolds that facilitated the development of more complex organic molecular systems. Atmospheric chemistry develops new complexity as volcanic outgassing continues under different climate conditions, and biological activity begins to influence atmospheric composition through photosynthesis and respiration. The interaction between atmospheric chemistry and surface chemistry creates new opportunities for photochemical reactions that generate complex organic molecules. These atmospheric surface interactions may have contributed to the inventory of organic compounds available for early biochemical evolution. Like a planetary chemistry laboratory awakening after millions of years of frozen suspension, the post-snowball Earth explores new molecular territories with the enthusiasm of elements finally free to interact in liquid solution under oxygen-rich conditions. only took 100 million years to establish the complex chemical systems that will support eukaryotic life. The chemical innovations of this period lay the foundation for all subsequent biochemical evolution, creating the molecular toolkit that will eventually enable photosynthesis, respiration, and the complex metabolism that powers multicellular life in an oxygenated world. Rivers that flow through time carry forward the chemical signature of Earth's ancient transformation as modern waterways continue to transport dissolved continents toward the sea with the same patient persistence that operated billions of years ago. The Amazon carries sediment from Precambrian rocks exposed in the Guiana Shield, their mineral grains weathered from formations that witnessed the first oxygenation events. The Mississippi transports nutrients from limestone beds that precipitated in Paleozoic seas when complex life first learned to build shells from dissolved calcium and carbonate ions. Contemporary river chemistry preserves isotopic fingerprints of deep time processes in the ratios of strontium, sulfur, and carbon that reflect the age and composition of source rocks being weathered in modern watersheds. Rivers draining Archean cratons carry strontium isotope signatures that record the formation of Earth's earliest continental crust. Watersheds cutting through Proterozoic sedimentary sequences transport sulfur with isotopic compositions that preserve evidence of ancient atmospheric chemistry and biological sulfur cycling. The global river flux delivers approximately 4 billion tons of dissolved material to the oceans each year, continuing the process of continental erosion and ocean chemistry modification that began when the first raindrops fell on cooling basalt 4 billion years ago. This modern chemical flux operates through the same fundamental processes of chemical weathering, physical erosion, and gravitational transport that moved Earth's first dissolved continents into its primordial seas. Only the scale and composition have changed. The basic physics remains unchanged. Seasonal variations in river discharge create temporal patterns in chemical delivery that echo the ancient cycles of wet and dry seasons, flood and drought, that influenced mineral precipitation and biological productivity in early ocean systems. Spring floods in temperate watersheds deliver pulse loads of nutrients and suspended sediment that temporarily alter coastal ocean chemistry. Monsoon-driven river systems in tropical regions create dramatic seasonal variations in chemical input that influence marine productivity patterns. The trace element chemistry of modern rivers connects contemporary marine ecosystems directly to geological processes operating in continental watersheds, just as hydrothermal vents delivered dissolved metals to early ocean chemistry. Rivers transport iron from continental weathering that supports marine photosynthesis in iron-limited ocean regions. Phosphorus delivery from agricultural watersheds recreates some of the nutrient-rich conditions that may have characterized early ocean systems before biological regulation of nutrient cycles. Pollution of modern river systems by human activities creates chemical conditions that paradoxically resemble some aspects of early Earth's water chemistry, including elevated metal concentrations, altered pH conditions, and unusual ratios of dissolved nutrients. Mining activities increase dissolved copper, zinc, and lead concentrations to levels approaching those found in Archean rivers, draining metal-rich volcanic terrains. Agricultural runoff creates eutrophic conditions similar to the nutrient-rich waters that supported early microbial blooms. Scientists study modern river-ocean interactions as analogs for understanding ancient chemical processes, using contemporary watersheds to test models of early Earth weathering and chemical transport. Mountain watersheds draining ultramafic rocks provide insights into the weathering of early continental crust dominated by mafic minerals. Volcanic islands offer opportunities to study weathering processes under conditions similar to early Earth's volcanic landscapes. Yet fundamental differences separate modern river systems from their ancient counterparts, reflecting billions of years of environmental evolution and the development of biological regulation of chemical cycles. Modern rivers interact with soil systems developed through millions of years of plant evolution and microbial activity. Continental weathering operates under atmospheric compositions and climate conditions dramatically different from early Earth environments. The biological mediation of modern river chemistry includes the influence of terrestrial vegetation on weathering rates, soil development, and nutrient retention. Plant roots accelerate mineral weathering through acid production and create soil environments that modify chemical transport between rock and river. Microbial communities in soils and sediments alter the oxidation state and chemical speciation of elements before they reach river systems. Climate change affects modern river chemistry through alterations in precipitation patterns, temperature regimes, and weathering rates that may provide analogs for understanding chemical responses to ancient climate variations. Warming temperatures accelerate chemical weathering reactions and increase the dissolution rates of carbonate and silicate minerals. Changing precipitation patterns alter the residence time of water in watersheds and influence the chemical equilibrium between minerals and solutions. The isotopic composition of modern river water preserves information about water sources and residence times that allows reconstruction of hydrological processes operating over time scales from seasonal to millennial. Oxygen and hydrogen isotopes in river water reflect the isotopic composition of precipitation and the degree of evaporation during water storage and transport. Carbon isotopes in dissolved inorganic carbon record the relative contributions of atmospheric carbon dioxide and soil respiration to river chemistry. Sediment transport by modern rivers continues the process of continental erosion that has operated since liquid water first flowed across Earth's surface. The annual global sediment flux of approximately 15 billion tons represents the modern expression of the same gravitational processes that transported weathering products from early continental fragments to Archean ocean basins. The grain size distribution and mineral composition of river sediments preserve information about source rock geology and transport processes. Estuarine mixing processes where rivers meet the ocean create chemical gradients and precipitation reactions that may resemble the interfaces between early rivers and seawater. The mixing of fresh river water with saline seawater creates complex chemical equilibria that influence the precipitation of clay minerals, carbonate phases, and metal oxides. These modern mixing zones serve as natural laboratories for studying chemical processes that operated at ancient river-ocean interfaces. The human modification of river systems through dams, diversions, and channelization alters chemical transport and residence times in ways that influence coastal ocean chemistry. Reservoir construction traps sediments and nutrients that would otherwise reach marine environments, recreating some of the chemical retention that may have occurred in isolated basins on early Earth. Flow regulation changes the temporal patterns of chemical delivery and creates artificial chemical gradients. Restoration efforts in degraded river systems attempt to recreate natural chemical transport processes by removing dams, restoring floodplains, and re-establishing natural flow regimes. These restoration projects provide opportunities to observe how river chemistry responds to environmental changes and may offer insights into the resilience and recovery of ancient aquatic systems following major environmental perturbations. Like threads connecting past and present in an unbroken weave of chemical continuity, modern rivers carry forward the molecular memory of Earth's transformation from a planet of metal-rich, oxygen-free seas to today's biologically mediated ocean chemistry. The water flowing past any riverside observer has traveled ancient pathways through rock and soil. gathering chemical stories written in isotopic signatures and trace element concentrations that span geological time. In the patient flow of rivers lies encoded both the persistence of physical law and the accumulating influence of life on planetary chemistry, a liquid bridge between the mineral earth of deep time and the biological earth of today. The ancient rivers slow their eternal conversation with stone and sea, their voices growing softer as they approach the vast ocean that waits at the end of all journeys. Here, where land meets water and time meets timelessness, the chemical stories carried from distant mountains dissolve into the planetary memory that holds 4 billion years of dissolved continents, weathered peaks, and patient erosion. The molecular dance continues in silence now, iron atoms finding their places in crystal lattices, oxygen molecules dissolving into solution with the same quiet efficiency they have practiced since the first cyanobacteria learned to split water under an alien sky. Each drop carries within its structure the accumulated wisdom of deep time, the knowledge of pressure and temperature, chemical equilibrium and gravitational flow, the endless circulation that moves substance from high places to low places with the persistence of physics itself. In the settling sediments at river mouths, layers accumulate grain by grain, preserving tomorrow's geological record of today's chemical transport. The same process that created the banded iron formations and cap carbonates continues in modern deltas and coastal margins, where mud and sand settle into sequences that future geologists will read like pages in Earth's continuing autobiography. The tidal rhythm slows, waves retreat from distant shores, and the chemical gradients that drive planetary circulation find their equilibrium in the vast reservoir of seawater that connects all landscapes, all climates, all the scattered fragments of continent and island across the turning Earth. The ancient ocean remembers everything, holds everything, transforms everything with the patience of geological time and the gentleness of water itself. Sleep comes to the rivers as it comes to all flowing things, not as an ending, but as a deepening into the stillness that underlies all motion, the quiet center around which chemistry and physics dance their eternal patterns. The water rests now in the embrace of gravity and time, carrying forward its molecular cargo into the dreams of a planet that breathes with tides and seasons, with the slow circulation of elements and the patient transformation of rock into soil, soil into sediment, sediment into stone. The story continues in silence, written in the chemical language that connects every atom to every other atom, every molecule to the vast symphony of planetary transformation that plays out over scales of time that dwarf human comprehension, yet remain as immediate and present as the water flowing past any riverside stone.